We're going to take a look at another example of modular exponentiation. In this case, we can see that the base and the power are getting larger, and this is going to be much, much bigger than 2 to the 128th. So we're going to carry out this algorithm by, once again, starting with the basic case. And the basic case is 12 to the first mod 9. Now 12 to the first mod 9 is asking again, what's the remainder of 12 divided by 9? Well, 9 goes into 12 one time and leaves a remainder of 3. So this is congruent to 3. Now once again, remember why we're using congruency here. We're also saying not only that 3 is the remainder, but that 12 minus 3, which is 9, is in fact divisible by 9. So we're going to iterate once again, and we're going to work ourselves up to the power of 128. So if you think about how long this is going to take, we're going to have to do a power of 1, 2, 4, 8, 16, 32, 64, and 128. So this is going to require 1, 2, 3, 4, 5, 6, 7, 8 steps, which is essentially 2 to the 8th power is equal to 128. This is going to become important because we're sort of working in this binary domain, as we'll soon see in the next example. So we're going to carry out now 12 squared mod 9. And 12 squared mod 9 is equal to 12 times 12 mod 9. And by our theorem, this means that if you take the product of two numbers, each of which individually is modded with 9, then that's congruent to the product of their remainders, which in this case is 3 times 3. Now 3 times 3 is 9, so this is equal to 9 here, and therefore I can still mod it with 9, again, because we want to get a remainder which is less than our divisor. In this case, this is congruent to 0 because 9 goes into 9 exactly one time. Now here's where things get a little bit more interesting. If we do now 12 to the 4th mod 9, oh, and I should have written, okay, there we go, 12 squared times 12 squared mod 9, and we can now take that as the product of the remainders of 12 squared mod 9. 12 squared mod 9 has a remainder of 0, so this is congruent to 0, and again 12 squared mod 9 is 0, and that's equal to 0. So the fascinating part here is that if we iterate another step, 12 to the 8th mod 9, and we're going to actually stop short of making it to 128 because we're going to see that this is just going to result in remainders of 0 across the board. So this is 12 to the 4th times 12 to the 4th mod 9. 12 to the 4th mod 9 is 0, and so we get again a product of 0 times 0, which is equal to 0. Now we can keep on going, but if you see what's going to happen now in the 12 to the 16th step, which is 12 to the 8th times 12 to the 8th, that's going to again be the product of 12 to the 4th 12 to the 8th's remainder, which is 0, and that's going to give us 0 times 0. And we're going to kind of keep repeating down to the end until we realize that, hey, the remainder is always going to be 0 across the board. If you get a remainder of 0, you can terminate the algorithm early, since that remainder is going to carry to the next step, which is going to carry to the next step, which is going to carry to the next step. Part of the reason why this is happening is because of the choice of our dividend, our base of our dividend and our divisor. There is a common factor between them. So let's make this a bit more interesting and say 12 to the 128th mod 7. So once again, we're going to repeat this process. We're going to say, well, 12 to the 1st mod 7 leaves a remainder of 5. And just again, we can verify that 12 minus 5 is just 7 is divisible by 7. In our next step, we'll do 12 squared mod 7, which is congruent to 12 times 12 mod 7, or I should say equal to, we're just giving an equivalency here, mod 7. And 12 mod 7 has a remainder of 5, so we have 5 times 5. Now before I write equals 25, I want to make sure that 25 cannot be divided again by 7, but 25 can be divided by 7 again. So if I do 5 times 5 mod 7, 25 divided by 7 is 21 with a remainder of 4. All right, so I carry that over to the next step. 12 to the 4th mod 7 is equal to 12 squared times 12 squared mod 7. And 12 squared mod 7 has a remainder of 4, so I get 4 times 4 here, which is 16, and 16 can be divided by 7 again, leaving us with a remainder of 2. And again, we just verify that 16 minus 2 is 14, which is divisible by 7, therefore our equivalency is correct. And we repeat again, 12 to the 8th mod 7 is equal to 12 to the 4th times 12 to the 4th mod 7. We could probably start skipping some steps here, and just instead of writing 12 to the 8th, we could just write 12 to the 4th times 12 to the 4th. But I like to keep track of my powers to make sure I don't lose something along the way. Now 12 to the 4th mod 7 is 2, so we get 2 times 2 mod 7. And, well, let's see, 4 divided by 7 is 0, remainder 4, so this is congruent to 4. Now we do 12 to the 16th mod 7. You can see this is not a super exciting process, but when a computer is going to do this modular exponentiation process, be it on a small base to the exponent value or a large one, this converges very quickly because of the fact that we're exponentially increasing our exponent. We're doubling our exponent each iteration. So this is 12 to the 8th times 12 to the 8th mod 7. And 12 to the 8th mod 7 has a remainder of 4, so we get 4 times 4 mod 7. And that's 16 mod 7, which gives us a remainder of 2. We're getting closer. Double that power. 12 to the 32nd mod 7 is equal to 12 to the 16th times 12 to the 16th mod 7. And 12 to the 16th mod 7 is 2, so this is congruent to 2 times 2 mod 7. And 2 times 2 is 4. 7 doesn't go into 4, leaves a remainder of 4. Now we're almost there. 12 to the 64th mod 7 is equal to 12 to the 32nd times 12 to the 32nd mod 7. And that's congruent to 12 to the 32nd mod 7 is 4. So 4 times 4 mod 7. And you can see that sometimes this process repeats. 4 times 4, 2 times 2, 4 times 4, 2 times 2, 4 times 4. And this gives me a remainder of 2. And our final step, now we're finally prepared to do 12 to the 128th mod 7, which is equal to 12 to the 64th times 12 to the 64th mod 7. And that's again the product of the remainder of 12 to the 64th mod 7 times that same remainder again, which gives us 4 mod 7, and 7 does not go into 4, leaves a remainder of 4, and so we found our final answer. So we could say that this right here is congruent to 4. Now, the beautiful part of this whole process is we could do this in our head. And that's not to say that we normally would, but it took something that was at first pretty much impossible to do. We could not even compute this longhand, or for that in our head, or longhand for that matter, without spending a tremendous amount of time. I won't define what I mean by tremendous, but you can only imagine how big that quantity is right there. 2 to the 128th is on the order of, I think we said 10 to the 36th or 10 to the 38th. So this would be a long string of digits. And we were able to take something that was fairly complicated to compute, and we were able to reduce it down step by step to where we could do it by hand. Now again, this is us, the human being, with a brain inside of our head. We were able to do this. Again, the analogy is when a computer does this, eventually numbers are going to get too large for that computer to calculate without performing something like modular exponentiation. In our final video, we'll go ahead and take a look at an example where our base is not necessarily a multiple, our exponent is not necessarily a multiple of 2.